Welcome to the Explainer. Look, if you're a really focused learner aiming for the absolute top of the JEE rankings, you are in exactly the right place. Today, we're taking off on a high-speed sprint to decode some of the toughest, most brutal concepts in mechanics and calculus using advanced concept illustrations. These are the high-weightage topics that quite literally separate the top rankers from the rest of the pack.
Let's be completely honest here. Have you ever just found yourself entirely stuck on wedge constraints? Or maybe totally tangled up in pseudo forces? Or sitting there staring blankly at complex calculus limits that involve definite integrals? Well, I completely validate that struggle. You know, these are notorious nightmare topics for a very good reason. But today, we're going to transform those nightmares into your absolute greatest strengths. We're building a systematic, rule-based path to mastery, tapping into the exact methods used to mentor students to AIR-1, 3, and 9.
Okay, let's dive right into this. Here is our roadmap for today. Number 1, decoding the constraint nightmare. 2, mastering the pseudo-force. 3, the power of graphs. 4, the Newton-Leibniz formula. And finally, 5, trigonometric general solutions.
Section 1, decoding the constraint nightmare. Let's tackle our first major physics hurdle, which is basically how bodies move when they're physically forced to interact with one another.
You see, understanding constraint motion isn't just about memorizing some dry formulas. Not at all. As our source material points out, this is the absolute bedrock foundation for advanced mechanics. When you've got blocks connected by strings passing through multiple pulleys or wedges sliding against each other, their movements are mathematically locked together. It's like a giant puzzle. If you don't map out this restricted motion perfectly right out of the gate, your Newton's laws equations will literally be dead on arrival.
So picture a classic system right now. Imagine you have a block on the floor and it's connected via a pulley to a hanging block. Pulley constraints require you to track the exact length of that string, which, of course, has to remain constant. If the block on the floor moves horizontally, well, that directly dictates the velocity at which the hanging block descends and eventually smacks into the floor. You absolutely must establish that geometric relationship first before you even think about calculating energy or forces.
And you know, these rules adapt to whatever geometry you're dealing with. Think about a ring constrained to slide strictly vertically on a smooth rod while attached to a larger falling mass. Now contrast that with a much more complex interaction where a block is forced to slide down the face of a wedge, which is itself moving. Whether it's a ring on a rod or blocks on an incline, the fundamental rule always holds true. The net speed of the object is a vector sum, governed strictly by the physical boundaries of that wedge or that string.
Section 2. Mastering the pseudo-force. We're now entering the realm of non-inertial frames. This is a concept where a massive percentage of students fail simply because standard physical laws suddenly don't directly apply. So to really master this, I want you to try something. Use a powerful psychological hook. As Ashish Arora notes in his preface, you need to think psychologically about the problem. Right now, create a hypothetical world in your imagination. Picture yourself standing inside an elevator, and suddenly, that elevator accelerates violently upwards.
In physics, that accelerating elevator is what we call a non-inertial reference frame. From the ground, which is an inertial frame, someone watching sees you accelerating. But from your perspective inside the lift, you feel like you're at rest, except you feel inexplicably heavier, right? To justify this changed condition mathematically so that Newton's laws don't just break down, we have to invent a mathematical correction. We have to apply what's known as a pseudo-force.
So the crucial point is how we actually deploy this thing. Here's your rapid-fire checklist. First, the pseudo-force is always treated as an external force. The formula? F equals negative m times a. Now, be super careful here. M is the mass of the object you're observing, but a is the acceleration of the reference frame itself. And that negative sign? It just means the force acts in the exact opposite direction of the frame's acceleration. Once you slap this pseudo-force onto your free body diagram, just like applying centrifugal force in a rotating frame, you can happily go right back to using normal Newton's laws, almost as if the frame were totally still.
Section 3. The power of graphs. Okay, we're crossing over from physics into mathematics now, and we're going to look at one of the most powerful shortcut tools in a top ranker's arsenal.
Here's the secret. Top-tier problem solvers don't always grind their way through lines and lines of tedious algebra. When they're confronted with complex functions, they visualize the shifts, the stretches, and the reflections.
Graphical transformations provide a brilliantly simple yet incredibly powerful approach to solving problems in a fraction of the time.
What's really fascinating here is how these transformations basically create a visual cheat sheet for exams. Let's say you take your basic known function f of x. If you add a constant a to the whole function, you literally just pick the graph up and shift it up by a units. Subtract a, it shifts straight down. If you subtract k from the x inside the function, you're delaying it, so you shift it over to the right. Multiply x by k, and you stretch or compress it like an accordion along the x-axis. If you memorize these visual rules, you completely bypass minutes of algebraic suffering.
Section 4. The Newton-Leibniz Formula. All right, this brings us to the climax of the explainer, and we're looking at the ultimate mathematical tool designed specifically for the most intimidating limits you will ever face on a paper.
First, let's quickly ground the abstract concept. Think about how functions can converge at a highly specific point on the y-axis. This is what a limit fundamentally is, right? It's analyzing how functions behave as they squeeze in and approach a specific boundary. But what happens when the function inside the limit is itself a definite integral with variable bounds? That's where things get really messy.
And that's exactly when you draw the Newton-Leibniz formula. Honestly, think of this as a highly specialized weapon. You just cannot evaluate a limit if there's a definite integral locked inside it, especially when it forms a 0 over 0 indeterminate form. Newton-Leibniz swoops in and allows you to differentiate that integral directly with respect to its variable bounds.
Let's watch how this builds when we deploy it step by step on a real limit. Step 1, plug in your limit value and confirm. Yes, you have a 0 over 0 form. Step 2, invoke L'Hopital's rule, meaning you've got to take the derivative of both the numerator and the denominator. Step 3 is where the real magic happens. You use the Newton-Leibniz formula to differentiate that definite integral. You just substitute the upper bound into the function and multiply by the derivative of that bound, then subtract the same thing for the lower bound. Finally, step 4, evaluate the resulting algebraic expression to find your final numerical limit. It's a bit of a sprint for sure, but it is incredibly elegant.
Section 5. Trigonometric General Solutions. We've officially arrived at the final resolution of our explainer. We've tackled constraints, we've tackled integrals, and now we absolutely must tame the infinite possibilities of trigonometry.
The critical distinction you need to make here is between a principal solution and a general solution. A principal solution is strictly fenced in. It really only cares about the angles between 0 and 2 pi. But as we know, trigonometric functions are periodic. They are many-one functions. They repeat their waves forever and ever in both directions. A general solution captures all of those infinite possible solutions across the entire number line.
And here is the core baseline rule that sets up the rest of the syllabus. If the sine of an angle theta equals 0, then theta equals n times pi, where n is any integer. Just think about that for a second. With that one simple, elegant formula, you have successfully captured every single time the sine wave crosses the 0 axis all the way out to infinity. You've basically tied up an infinite number of solutions into one neat, perfect little package.
Before we wrap things up today, I want to bring us back to the core philosophy of this entire explainer. As we highlighted earlier, create a hypothetical world in your imagination. Think psychologically about the problem rather than just memorizing theory. Mastering these AIR-1 level concepts, whether that's seeing the graph shift in your mind's eye or literally feeling the pseudo force in that elevator, it requires active, vivid visualization.
So I want to leave you with a bit of a challenge for your next study session. When you sit down with your modules later, are you going to let constraint equations and definite integral limits remain a nightmare? Or will you apply these advanced rules, visualize the systems, and calculate your way right to the top ranks? The choice and the tools are now totally yours. Keep learning, keep visualizing, and I'll catch you in the next explainer.